Right, this is a continuation of that last video. We were going to draw our diagram to represent what was on the balance. So here we've got 2 tins of tuna on one side and 1 tin of tuna on the other side. And we call that one F1, and we can call that distance there, from there to there, D1, which is distance 1. We can call this one F2, which is 1 tin of tuna, and that's a distance there, which is which is D2. Now, let's imagine we didn't know what F2 was, but we knew what D2 was. Let's say this was 150 mil, and let's say this was 300 mil. So for equilibrium, F1 times D1 must equal F2 times D2. So we know F1 is 4 newtons, because that's 2 tins, 2 newtons each. And we've said that D1 is 150 millimeters. So we can put the figure, and we know that we don't know F2, and we said D2 was 300 millimeters, which is approximately where we are on that scale. So now we can put the figures in. F1 times D1, 4 times 0.15. Don't forget, you've got to deal in meters, so it's 0.15, equals F2 times 0.3. So I'm after F2. So transpose. To get rid of 0.3 on this side, I have to divide by 0.3. So you divide by 0.3, they cancel out. So you do that on this side, 0.3. And that should come to a sensible number. Four times 0.15 divided by 0.3 equals 2. So 2 equals F2. And we've just proved that 1 tin of tuna weighs 2 newtons. Okay? Right, so let's have another example. I've got a piece of steel work. There's my fulcrum. I have, say, 270 newtons force on that side, and that's 1.2 meters away from the fulcrum. And I've got a force of, let's say, 130 newtons that way. I want to find out what D2 is. Let's say we know D1 is 1.2, we know F1 is 270, F2 equals 130. For equilibrium, F1 times D1 equals F2 times D2. Put the numbers in. 270 times 1.2 equals 130 times D2, which we're trying to find. So to get rid of this 130, I need to divide this side by 130 and this side by 130, they cancel out, to find D2. So let's have a look at that one. 270 times 1.2 divided by 130. And that comes to 2.49. So this has to be 2.49 meters away to keep this system in equilibrium. So that is 2.49 meters, virtually 2.5 meters, isn't it really? Okay. So that's one example. I think I might have time just to do another one. Let's say two forces, because the same applies to two forces on one side. So if you've got a piece of steel, you've got F1 there, 10 newtons, F2 is 20 newtons, and I want to put a force here, F3, and this force F3, I'll say that one is 3.6 meters. This distance here we'll say is 0.5 meters, and this distance here is, let's say, from the fulcrum is 2 meters. So F1 times D1 plus F2 times D2 equals F3 times D3. Put in the numbers. F1 is 10, D1 is 2, we add that to F2 and D2 is 20 times 0.5 equals F3 times 3.6. So that's 20 plus 10 equals F3 times 3.6. 30 equals F3 divided by 3.6. So F3 needs to be 30 divided by 3.6 is equals 8.3 newtons. Okay. So for equilibrium to occur in a system, all the forces on one side and distances must add up to all the forces and distances on the other side. So basically you can now find one unknown, usually either a distance or a force, to calculate that correctly. Okay, I'll put some problems on solar, so take a look at those, and then we'll move on later to torque. Thanks, bye now.